Hello everyone. In this session, I am going to look at the different kinds of partition based clustering methods. We know that on a broad scale, I can divide the clustering methods into two kinds. One is a partition based clustering methods. The other one is the hierarchical. So again within each one, right, just as a quick reiteration, the hierarchical clustering primarily focuses in terms of maximizing the distance between the clusters. So all the algorithms, hierarchical, they maximize the distance between the clusters. They use either the top-down approach or a bottom-up approach. So based on that, we get different kinds of solution. Whereas partitioning based methods, they generally the main target for them is minimize the distance within the clusters. So again, there are different kinds of algorithms which are targeted towards the partitioning base. So this is where in this session I'm majorly focusing on four different kinds of mechanisms. We have already discussed that the primary or the most important clustering solution going with the partitioning base is the k-means clustering. So we'll try to apply, we'll take one single data set, we'll try to apply the clustering solution, the clustering algorithms, these four different clustering algorithms on the same data set, see what is the kind of clusters that are getting created. So we'll talk about k-means clustering, then we'll look at Clara algorithm again for doing the clustering process. We will also look at the PAM algorithm for doing the clustering again. And finally, we could also look at the kernel weighted k-means algorithm. It's again a slightly different structure. So four different kinds of algorithms. We'll try to execute them on data set and see what is the way the entire data set is getting grouped. So k-means. We have been talking in the k-means cluster that I have to really come out with how many clusters do I really want, right? So by default, I have to give some number of clusters. So let's say initially, let me go ahead without talking about this. Let me go ahead in terms of identifying some number of clusters. Initially, I'll take a data set, right? I'll take a data set. I will, let's say, specify three clusters for this data set, and let me completely split the data. Then we'll see how do we typically look at what is the optimal number of clusters that I may have to go with, right? So initially, let me first run the k-means solution. Then let me try to see how do I really plan out the whole process, right? So let me let me first get the data, some basic initial stuff. So I have got the data relating to the stocks. I'll tell you what this data is all about. So let me look at the dim of stocks. So 1713 rows are there, 6 columns are there for this. If I look at the summary of stocks, this is the summary. Initially I have the name, right, symbol name. Then we have closing. The closing price values ranging from 0.05 to almost 49,949. So that's the kind of variation we have on the closing prices of the stocks. Changes wise, zero of them. Okay, it is coming out to be not a number. It's coming out to be the change is coming out as a group, a categorical variable. This is something which is which I really need to look at. Why? Right? Change is coming out not as a number. Then total traded quantity is a number having a minimum value of 1 to a maximum value of 26,000, or sorry, to 26 million. So total traded quantity went into 26 million. Similarly, traded values, the same thing, values ranging right from 0 to 5.75 into 10 to the power of 9. Total trades also went in from 1 to 145,000. So let me just see why the change is coming out to be. First, let me look at the structure of stocks to see what it is. So the change is coming out to be a factor. So let me try converting it. So let me say stocks dollar change. Let me see what it is. So there are some positives, there are some negatives. So 1589 levels are coming out. So let me change it. Stocks dollar change is, first let me convert it into ASDAT character. Stocks dollar change. Now this from levels it is getting converted into a character, and on the top of this I will apply as dot numeric. Now I'll apply as dot numeric on the top of it. See if, okay, if there are NAs are there, they are entered by coercion. Let's see what has come out. Why this NAs have really come out. Alright, let's see why the NAs have typically come out. Now let me talk about the structure of stocks. Okay, so the change is a number which is showing some positives, some negatives kind of stuff. Fair enough. Let me look at the summary now of stocks. Right, let me take the summary of stocks. Okay, there is one NA. Better let's remove the NA. That's one of the prime reasons possibly. So let me make it as stocks. I'll take it as NA dot omit stocks. So whatever that one single NA was there, I am removing it. Now when I look at the summaries, okay, now it looks pretty firm. We have closed, we have changed, traded quantity, traded values, and the total number of trades. Now what I really want to look at is these 1712 stocks that I have. This is what is the situation of the stocks on one single day. So they have closed at the closing prices of these 1713 stocks is more like this. On an average, the closing price is around 552. The median is around this. The third quartile is around this, and so on. On one single day, this is how the changes. The minimum was 38% drop to the maximum was 22% increase in one single day. Similarly, these are what are the behaviors of the stock of all the 1712 stocks on one single day. Now, based on this one day's performance, I really want to group these stocks as a natural grouping process. So this is where I found that cluster analysis could be a much better solution. Obviously, I will not use symbol. So let me even remove the symbol as well from the list. Otherwise, I could stocks 1, let me call it, wherein I am taking stocks, I am taking a subset, all the rows but only all the columns without the first column. So that's how I am getting my stocks 1. So there are 5 columns based on which I want to group them. So the model 1, which is let me call it as model 1 underscore k means. I did not do any kind of optimal solution or anything, but before I execute it, it's better that we normalize the data, right? So this is where once more let me take it as stocks 1. Let me normalize it by doing a Z scale Z-score computations for all of them, because I don't want the size to be impacted, because I have total traded value running into almost 10 digits kind of numbers, whereas the change is hardly any number, right? It's very close to zero. So that's where I don't want the size to be impacted in my cluster computation. So this is one reason I would like to do a scaling of the stocks one. So I'm doing the scaling of the stocks one. So now quickly I can look at the summary of the stocks one to look at the scaling process. I could see now all of them came more or less in the same range, 0 to 26, even after the scaling here. This is what is the numbers. Then I have minus 10 to plus 5 in case of change. Traded quantity is minus 0.32 to plus 13. Traded value is again minus 0.3 to plus 15, and total number. So almost the ranges are not too far off from each other. Now based on this, I want to execute my cluster analysis, the k-means cluster. So let me call model 1 underscore k-means. So I am using the simple k-means formula, k-means function, where I am taking stocks 1. This is what is the input that I am taking. I require 3 clusters to be created. So let me just go with this much itself. The number of clusters is 3. So my clusters got created. So let me see what they are. Model 1 underscore k means. So this is how the clusters got created. So all the observations have been created, have been taken into different clusters. We have 3 clusters. One is having a size of 100. The second one is having just a size of 9. And the third one is having a size of 1603. But if you see, the closing prices are very high for these 9 of them. The change is very much negative, so they have fallen in price. The total traded quantity is slightly negative. The total traded value is again a little bit positive, but the total number of trades is slightly negative. But if I look at this cluster 1, very interesting stuff. The closing is somewhere around 0. They have changed by approximately 10%. But you could see that the total traded quantity is very high, total traded value is very high compared to the others, and even the total number of trades is very high. So this 100 is looking like a completely different set of stocks altogether. We'll see what they are, but that is what is one solution that my k-means cluster is giving. So I'm getting my cluster means, I'm getting the cluster vectors, each one what kind of clusters, and I could see this is the measure within the cluster sum of squares. So the sum of squares of this particular cluster is this much, this much, this much. So between the cluster's sum of squares is occupying around 41% now, and in the partitioning algorithm we see that within the cluster sum of squares should be as minimum as possible, which means the between the clusters sum of squares I want to increase it to whatever extent possible, right? So if I really want to see model 1 underscore k means dollar, I want let's say within sum of squares. So these are the numbers within the sum of squares. The total sum of squares we already have between sum of squares. So I can very well identify. So these are the ones that are within. So I can even find out the within sum of squares. So in this case it is looking like 5049. This is the within sum of squares as a part of the clusters when I have gone with 3 cluster solution. Now the same way I can go ahead with 4 clusters, 5 clusters, etc. Right? So let's say the whole process, let me do a model 2. Let me do a model 2 with 4 clusters, everything remaining the same. I'm doing the model 2 k-means with 4 clusters. And now I want to go with model 2 k-means within sum of squares, which is coming out to something around this. So these are the within sum of square that I am getting. So within sum of square should be as minimum as possible. So when I am going with the summation of all these, this time I am getting the within sum of squares is 4300, which means the gap got reduced now. And if you want, you can look at the between sum of squares as well. So you could talk about model 2 underscore k means dollar between sum of squares, right, which is working out to 4247, and I could also take the total sum of squares. So wherein I can take k means dollar. Okay, I have total to within sum of squares, but let me take total sum of squares. So I'm getting the total sum of squares is this much. So overall I could simply take the ratio, which is giving me the ratio is giving me 49. So the within sum of squares has actually got maximized from 41, it has gone to 49. So the cluster solution is much better here. 4 cluster solution is much better compared to a 3 cluster solution. Now, so like this, where all, how to what extent I can go. Now this is where we have a mechanism of identifying what would be an optimal number of clusters for this particular data. Now that I can get in using the k-means runs, which is there as a part of the FPC package. So let me install the FPC package. So this is not doing any k-means. It is having the different functions which can really give me what would be the appropriate number of clusters for this kind of a solution, right? So it's not doing any kind of k-means, it's not doing any kind of a clustering. It is only bringing out what would be the appropriate number of clusters for this kind of a solution. So let me load this. Loading FPC. I've done with it. So we have the data in place. We have this package in place. Now I can start the assessment of the model. So let me use the k-means runs. So if you see in this package, I'm more interested in a feature called k-means runs. The reason being, this k-means runs, this calls the function k-means to perform a k-means clustering, but initializes the k-means algorithm several times with random points from the data set as mean. So it keeps rotating the process. It's not just a one-time execution. It is selecting different kinds of random points from the data set. So as we said initially, the k-means works by randomly selecting different points, and from there the groupings happen. But this k-means runs process, it executes the same k-means internally, but it keeps on rotating the process. And here it is more robust. It does not allow you for the occurrence of empty clusters in the algorithm. and the number of clusters, it keeps playing around. 3 clusters, 4 clusters, 5 clusters. It estimates the number of clusters. There are different kinds of indexes that we can go with. Either Kalinsky-Haraba's index, which is called as a CH index, or average silhouette width. So these are different kinds of mechanisms with which I can really come out with what is an optimal number of clusters. And there are different kinds of tests. Judah test is applicable to decide whether there should be more than one cluster as such. So should there be more than one cluster or not? And again, estimating optimal number of clusters can be done either by Kalinsky-Haraba's index or average silhouette width. So I can use any one of these mechanisms to typically come out with the optimal number of clusters for this particular data. And if you see, by default it requires the data. So I have the data with me. It should be a numeric matrix of data or an object that can be coerced to such a matrix. Right, I can have a numeric vector or a data frame with all the numerical columns. That is what I have, so I can directly give the data. Then I have to specify the k range, how many clusters, which are to be compared with average silhouette width criteria. So I can give, let's say, 2 to 10, 2 to 20, so that it will perform for all possible combinations and tell me which solution is the best, which optimal number of clusters is best. The criteria for the selection, right? So in some cases I can use average silhouette width, or probably I can use Kalinsky-Haraba's index. So whichever is the index that I am applying, I have to specify it either as CH or ASW. Then if I have any number of maximum number of iterations, the maximum number of runs, by default it executes 100 different runs before giving us the solution. So these are some of the important things, right? And probably the other thing, the crit out. So the criteria output is, the criteria value is printed out for every number of clusters. So I'll set the crit out equal to true here, so that I'll get the criteria to be printed. And even the plot, if true, every clustering resulting from a run of algorithm is plotted. So for each one, so I don't need to plot each one, because there's approximately 100 different things that are going on. So I would not be plotting those. So let me do one thing. Initially, let me get started. This we will go ahead with. This will go ahead with Kalinsky-Haraba's index. So I'll call it as CH, the number of clusters K, which I'm going ahead with K means runs, wherein I'm taking my data, which is stocks 1, and I have to specify the range. So let me take K range from, let's say, 2 to 20, right? Let there be a n number of clusters. So I'm considering 2 to 20. Then I require, if I specify the runs, fine, otherwise it will take 100. Then I can also take my criteria. So I'll take it as a CH criteria. Then after that I'll change it to ASW and check it out. And I also want crit out, which is the printout of the printing out of all each of the clusters. I'm setting it to true. So based on that, the k-means runs is typically performed. So for each of the combination, it will have to execute this, and it will have to give me the result. Yeah, this is what it is. So the 2 clusters solution, the value is 715. In case of 3 clusters, it's 594, so on. So I am seeing the optimal number of clusters is the one that is having the highest CH value. I could see in this case two cluster solution is having the highest CH value. So that's the optimal thing for me. I should choose two clusters rather than going with three clusters as the way I have worked out earlier. Similarly, I can use another solution which is the ASW solution to check out. Right, so let me go with ASWK. The only difference now is instead of criteria equal to CH, average sellout width. I'm trying out even this kind of a solution to see which number of clusters is more and more optimal or appropriate for this particular data. So even through this mechanism, so this is taking some time. So, okay, so if you look at this mechanism, compared to two clusters, it's saying three clusters is much better. If I'm going with this logic, 0.747. So the three cluster solution is coming out slightly better because the value is slightly higher in case of a three cluster solution. So it suggests that if I'm going with k-means clustering for this particular data, it's better that I go with three clusters rather than two clusters, and that is what initially also we have worked out in terms of going ahead with three clusters itself. So I could very well go ahead in terms of the three clusters, right? I have already executed the k-means. Now we can see the k-means. There are different kinds of algorithms again within the k-means. If you see here algorithms wise, I can just take k-means, the data, how many cluster centers do I need? Right now it is saying 3 or 2. And the algorithms that we can take, either Hartigan Wong is an algorithm that I can choose, or I can choose Lloyd or 4G or McQueen. These are the different kinds of algorithms that we are talking of, right? Maybe abbreviated. So Lloyd and 4G are the alternatives for one single itself. So I can very well go with these different kinds of names. So if I am going with this particular name, so let me try all of them, right? So now let me go with 3 itself. So model 1, let me call it, wherein I am taking k-means. I have taken stocks 1 with 3 clusters, and the algorithm I am finalizing as Hartigan-Wong algorithm. Okay, so this is how my model got created. Now I can fit each of the observations. So let me look at the plotting of the stocks 1. So I'm plotting stocks 1 separately. So wherein I am selecting the columns as model $1 the cluster that they are allotted to. So let me call model 1. So for each cluster there is a separate plotting that is happening. So I could see that the ones that are, so we are getting, because all of them are numericals, we are getting a few of them in greens. So the ones which are towards the downside in terms of change, so we can look at with respect to each one of them. So we are seeing that the close, change, different kinds of graphs are typically coming out where we are talking about the plottings across all the stocks 1. and where I am going with the clusters. So this is one way, or probably I can very well look at observing. So let me call what is my model 1 first. Rather than doing this, let me call my model 1. So this is how the model 1 is coming out. I could see here. So these are the cluster means. 337 are there in one cluster, 1303 in the second cluster, and 72 of them are there in the third cluster. And I could see here, these are the ones which have closed very badly, right? I mean, very smaller closing prices. They have changed very drastically positive. Total traded quantity is much higher positive. But if you look at the third group of 72 elements, they have a very high traded value, very high number of trades. The traded quantity is also much larger. So that 72 are completely different set of curve. And now overall it so came out that the within sum of squares, the between sum of squares is 38.2. Right, so we are trying to compute the between sum of squares, which has worked out to 38.2%, and that is what is the solution. So now I can very well integrate these clusters to my original data itself. So stocks dollar k means, right, with the original stocks I am trying to take the stocks dollar k means, or probably let me take it as, let me take them stocks 1, let me take it stocks dollar k means itself, wherein I am allotting, or let me keep them, after that we'll assign all of them. Stocks $1 k means, the names are not there, that's the reason I am not considering. Let me just check what is the stocks. Dim of stocks, so 1712 and 6, okay, fair enough. So let me add to this itself stocks dollar k means, I'm adding one column to it, right, which I am simply taking it as model $1 cluster. Okay, now let me see the dim of stocks. So 1712 rows, 7 columns, and if I look at the head of stocks, it's working out to these ones. So if I really want to see the stocks where, right, I want to look at where stocks dollar k means, I want to see which of them are actually 3 equal to 3. So only those rows I want, and I want to take all the columns. So here I could see these are those stocks which had very high amount of trade, total traded value, total number of trades, traded quantity. If you see, these are all could be the bigger ones. The A-Ban, the Adani Ports, Adani Power, right? Akash Optical Fiber, Ashok Leyland, Asian Paints, Aurobindo Pharma, Axis Bank, etc. So these are the 72 stocks which are almost the bigger ones which have made to this list. So this is one way I could see. For this is the one kind of clustering that I'm creating. I can look at each of the variables, how it is differing across the clusters, right? So that's what it is. So we'll see all other algorithms later on. So we have loaded the necessary package, get the data, We have taken only numeric data. If there are any factors, we need to convert it into dummy variables. So we have performed the minimax normalization. We have actually done the z-score normalization to remove the size factor, right? We did not look at the minimax. Probably that's one more solution that we can very well look at. So we have given the number of clusters, though in reality we did not go with starting with number of clusters. We have used the k-mean runs, wherein we looked at the Kalinsky-Harabaz index or even the average sellout width to finally come out with what is the optimal number of clusters. So here we got them as 2 clusters, here we got them as 3 clusters. I could actually take the within group sum of squares for each of the solution, and I can actually create a plot, and that plot is what? So if you see, if I had gone with 2 clusters, this is what is the within sum of squares, right? Within group sum of squares. Then so for 2 clusters, what is the within sum of squares? For 3, what is the within sum of squares? Actually we have to go for, let's say, up to 20. What is the within sum of squares? What you find is the within sum of squares actually keeps decreasing like this until sometime it decreases sharply, and after that it becomes more or less flat. So wherever it is becoming more flatter, this is the elbow part. Wherever it is becoming more flatter, which means the within sum of squares can't be decreased any more further. I'll typically use that as my optimal number of clusters. But of course here we have relied mostly on the ASW mechanism to identify the number of clusters. And once we have identified the number of clusters, we are fitting the model using the k-means. So if you want, you can plot some specific variables or plot all the variables to finally find out which cluster fitment is looking more apt. Here my third cluster is looking very apt with 72 observation. All of them trying to come from the most bigger kind of companies itself. Now the next thing, once we have seen that k-means has done this kind of a job for this data, then the next thing I can move on to is the another algorithm, which is the Clara algorithm. The Clara algorithm is coming from the cluster package. So I have to install the package cluster. I should be having it, but anyhow. So I'm installing the cluster package. Right, I don't need to repeat how many clusters do I need to go with. I'll go with 3 clusters itself. But yeah, here the definition of the number of clusters, I can't use the k-means runs. K-means runs function in FPC, it actually executes the k-means internally, and based on that it identifies the number of clusters. But here, because we are not going with the k-means algorithm, I can't use k-means runs to identify the optimal number of clusters. So here I have another function to use, which is the PAMK. PAMK. PAMK is the name of the function that I can use for identifying the number of clusters. So I can't directly, so this is what I was mentioning here, the PAMK method is going to give me the optimal number of clusters here. But okay, once this is installed, I have to load the cluster package. So here we have a function called Clara. Clara, so let me look at what this Clara function is all about. Computes a Clara object representing a clustering of the data into k clusters. So this is what it is doing. It will take X. X is a data matrix or a data frame. So it's a data frame. Each row corresponds to an observation. Each column corresponds to a variable. So I can directly give it as a data frame. So the overall data I can give as an input to it, right? Missing values are also allowed. So all the variable names should be numeric. That's the only thing in case of Clara. And the k is the number of clusters. So I have to specify the number of clusters. Now that I know, I can very well say I'll go with k equal to 3 and continue the process. Then there is nothing much to do. But on the other side, if I really want to go with identifying the optimal number of clusters in this case, then I have to use the PAMK algorithm as well, right? PAMK function. And for me to use PAMK, if you see, this calls the function PAM or Clara, one of them, to perform partitioning around the medioids. So here the partitioning is happening around the medioids, not around the means or centroids, with the number of clusters estimated by optimum average sellout width. So here we are using average of ASW kind of a mechanism, or even Helsinki-Haraba's mechanism. So again, here also the same thing, but the only difference is the data that it is taking, the data frame that can be coerced into a matrix or a dissimilarity matrix. So the dissimilarity matrix, or I can directly give the data itself. So let me try first. Let me try to use the PAMK, right? So let me call it as PAMK, wherein PK let me call, which is the number of clusters using this PAMK algorithm. So I'm using PAMK as the name of the function, right? The data that I'm taking is stocks1. I'm taking this data called stocks1. I can give the k range, which is from 2 to 20, right? Criterion, as I have given earlier, I can give the criteria as ASW, which is average sellout width. I can take crit out equal to true, so that the criteria can be printed. And here, as we have said, it will execute either the PAM or the Clara function. So I have to really give this, is it using Clara or is it using PAM? Right? So we are using Clara, so I'll set use PAM equal to false. So I'll use this function use PAM, this argument use PAM equal to false, and next time when I'm doing the same with Clara, I'll say use PAM equal to, when I'm doing with PAM in the next mechanism, in the next method that I'm executing, then I'll take, so here in this case, let me check what is happening. 2 clusters is a big solution, 0.88, but again, after that, the numbers have fallen. So this has said that 2 cluster solution is much better rather than a 3 cluster solution. So I can very well go ahead. I can very well go ahead with the 2 cluster solution itself. Or if I want to be more and more looking across, let me go ahead with the 3 cluster solution, so that I can see how the clusters are getting comparable across the k-means as well as Clara. So let me say model 2, which is the Clara model. I'm taking it as Clara stocks 1, and I'm setting, let's say, k equal to 3. So my model is getting created, my Clara model. So let me see how it got created. So I'm putting plotting of model 2, which is giving me, so this is what it is giving with respect to one set of components. So these two components, component 1 and component 2, only 2 of them are plotted. They explain 68.55% of the point variability. So 2 components together. And this is one more plot that we are coming out with, the average silhouette width is coming out to 0.65, and this is the cluster solution that is coming out. In cluster 1, we are seeing these are the observations, cluster 2, cluster 3. So approximately in cluster 2 and cluster 3 we don't see too much. So that is what we find on an average by taking n equal to some 46. So let's see how it is working out for us. Right, so let me take what all outputs the Clara is giving so that I can evaluate the things in this process. Right, so I can very well take out the model 2. The model 2 is saying it has taken 3 clusters. These are the medioids, so it's not going with the centroids, it's going with these as the medioids. Now you could see there's a very high closing price. But if you look at this, the second one, these are the medioids. You see that the change is very positive. The total traded quantity is very much positive. Traded value is very much positive. Total number of trades is very much positive. Right? And cluster sizes are 1586 here, 125 here, and only 1 in the third group. So that 1 is getting identified as an outlier altogether going with this process. So the second cluster could be very much important for me, right? With this 125 stocks is coming as a part of the second cluster. So if I want to see what are those clusters, I can very well see the clustering, right? Let's see model $2 clustering to see. So this is the way each of the data has been put into different clusters 1, 2 and 3. So what I can very well do is I can even combine this. So stocks dollar Clara. I'm adding these to stocks dollar Clara again, wherein I can very well go ahead with the allotment model $2 clustering. So another addition. So now let's look at the head of stocks. So this is what is the Clara based clustering that has come out. 2 is a very important cluster here. So let me take the shortlisting again. Stocks, wherein I am looking at stocks dollar Clara is equal to 2, comma, I am looking at all the columns. If I look at this, I could see that these are the 125 companies that have come into this list. As per the K-means, yeah, they are all not into the third category. Some of them are in the first category as well. 3i Infotech came into this Clara 2. Similarly, Aptech came here, Arvind Mills came here, right? And I could also see Bank of India coming in. Then Bharti Airtel, BHEL, they are there as a part of the cluster 1 there, whereas here they came as a part of the cluster 2, which was more or less equivalent to your cluster 3. So we get BS Limited. So again, most of them are big firms. Cipla is here, Crompton Greaves is here, right? We could see DHFL coming into this group, Dish TV coming into this group, which were not there as a part of the original solution. So we could see more or less almost all the ones that are there in the third group, they are there in the second group now. But a few of them which were in the first cluster through the k-means mechanism, they are representing the cluster 2 in this mechanism. So again, different clusters are classifying the data in different mechanisms. Right. So now let me read through the content part again. So this is what prepare the data. We have prepared it. Then do an estimate and assess the model. So exact number of clusters, we have got it as 3 by implementing the PAM with the average hill house width, and we have fitted the model, and finally we have to visualize the result also, and again we have applied it back to our data to just see which groups are more or less appropriate. So that's one more way I can, one more algorithm for clustering purpose. Then I am doing the PAM algorithm, which is also more or less similar. It's also there as a part of the cluster package. The input that it takes is also more or less the same. I need to give the number of clusters again. The data preparation is more or less similar. So what I really need to do only is, when I'm going with PK1, I'm going with PAMK again, but I will not put the value equal to false. Use PAM, I have to put it as true. That's the only difference. Now I am setting PAMK, stocks 1 is my data. Then the K range, I can take it as between 2 to 20. So the whole range I have taken. Again, I'll take the criterion as ASW, which is the average cell house width. And I'm also considering the printing out of the criteria so that I can evaluate quite comfortably. So I'm saying crit out equal to true, and use PAM. I'm not using Clara here. I'm using PAM. So that's where I'll to identify the number of clusters, I will set use PAM equal to true instead of false. So let it identify how many are the optimal number of clusters. Still I can use the same 3 and try to fit it with the data. So let it identify the optimal number of clusters for this data set, for this kind of algorithm. So now it has identified the different number of clusters through this optimal number of clusters. Here also it is coming out that the cluster solution with 2 clusters is more and more optimal. Otherwise probably it should, the next best is a 3 cluster solution. But still I want to go with 3 clusters so that we can compare the things, whereas when you have looked at earlier the 3 cluster solution in case of Clara, it has taken only one observation into the third cluster. So that's where the classification will not come out to be anywhere better if we are not going through this kind of a process, right? So I could really look at going with 2 cluster solution or even a 3 clusters. So let me say model 3, where I am using the PAM algorithm for the fitment, where I am using the stocks 1, which is my data set, and I am giving the number of clusters as 3. So this is the model solution that I have got. So I can check the model by typing model 3. So it is giving me that this is how it has categorized. Again, these are the medioids, right? Initially it started off with these values as the medioids. Then if you see here the closings, all of them are showing some negatives, but very much the change is these are having 0.69, a big positive changes. But if you look at the other things, total traded quantity, this is looking like very high traded quantity. The traded values are also very positive. Total number of trades is also very positive. So it looks like the group 2, the cluster 2 is more or less those bigger firms. But going further and looking at So this is how it has used. I could really look at these is the cluster info, right, and the number of elements that are there in each of the clusters, the cluster info, right. If I look at the summary of model 3, this is what is the summary that it is giving. So it's saying average silhouette width for each cluster is this much. Overall, the average silhouette width has come out in this way. And before getting in here, you could see that the summary is giving me that, okay, the clustering vector, yeah, the size 1062 are in this particular cluster, 175 are in cluster number 2, and 475 are in cluster number 3. So that's how the three clusters got classified. Now what I can very well do is I can very well append the same. So I'll do stocks dollar PAM, wherein I'm taking how do I get the clusters? Let me just check what is that I'm getting through clusters. Model $3 clustering, I suppose. Yeah. So I'll do stocks dollar PAM. I'm assigning it as model $3 clustering. So now one more column. So I'll look at head of stocks, which is telling me, okay, this is how the PAM got classified. Now I will check for those stocks whose PAM value is equal to 2, because those are the ones that are getting classified as the bigger stocks out here. So I will set stocks dollar PAM is equal to 2, and I'll take all the columns. So based on this, it is working out that majority of them, if you look at the ones who are having PAM of 2, Free I Infotech, so majority of them which are 2s in the Clara, they also got 2 in the PAM. But surprisingly, instead of 1 and 3, even there are a few 2s which were there in K-means, they also got classified as a part of the PAM, right? So which algorithm is much better? We have to really see and assess how it really is fitting to our data, right? There are some tools, again, these are actually the big firms itself, the Adani Enterprises, again a big firm, right? We also see a few other things, probably Apollo Hospitals, which got classified as group 1 under Clara, but under PAM it has got classified as group 2. So I can very well look at Apollo Hospitals as well in the list. So this is one more kind of a classification that is being produced by the PAM algorithm, right? Then, so we have done this whole thing. If I want, I can even do a cluster plot, which is the plotting of the entire clusters separately. So I can do a plotting of model 2, which was the Clara algorithm. So this is how the Clara algorithm has done the plotting, saying 68.55% of variability with component 1 and component 2, right? And these are the way the clusters are getting named. So this is one cluster, this is another set of clusters, and we have the third one which is having the maximum difference between the clusters. Whereas the same thing, if I am going ahead and plotting for model 1, okay, model 1 is k-means, so I can go with model 3. Now the model 3 is giving me these. So this is one cluster, right? Cluster plot, I can even get the names of the clusters also. Probably let me just see something more as a part of cluster plot, right? It draws a two-dimensional cluster plot. So I'm giving an R object, right? The the class is Pam or Clara, I can very well give to it. So that's what I have provided. And the optionals, okay. All right. So it is doing the plot. So this is how the plots are differentiated. So when I am going with class plot of model 3, this is how we are getting the three clusters. One cluster is somewhere here. The other cluster is having a maximum number of differences out here, whereas for other cluster, we are seeing good number of elements are found at this stage as well. So that's how the clustering is typically performed. Then I'm moving on to another. I'm moving on to another mechanism, which is what we talked about as the kernel weighted k-means. So the kernel weighted k-means is another extension to the existing k-means algorithm for clustering itself. This is also a partition based. But before we go there, if you summarize it, so based on the means when the data is partitioned, we have a k-means algorithm where the centroids are typically computed, whereas based on the medians when the whole algorithm is computed, we had a Clara algorithm, we have a PAM algorithm, which have done based on the medioids instead of the centroids or the means. So there is a change in a mechanism between these. And similarly, I can look at the kernel weighted k-means algorithm. So the sample data is actually projected into a non-linear feature space. A kernel is typically used. This is what we have done even in case of support vector machines. So there is a mapping of the data into a non-linear space using different kinds of kernels. So that's the same thing we are doing here as well. So it can identify the clusters even if they are not linearly separable also. If the relationships between them are completely non-linear, still I can use this kind of a mechanism to identify the groupings between the data. So we have for this we are using a package called kernlab, and out of which I would be using a function called kkmeans. So within the kkmeans again I have to specify what is the data that I need to cluster and how many cluster centers do I require. Instead of k-means, we are using kernel weighted k-means, so that's where we are calling it as a kk-means. The process is more or less the same, right? We are taking the data, we are taking the clusters, centers, and based on that, we are creating the model. So let me go ahead and try to implement this model. So let me first install the kernlab package. So installing this kernlab package. Right. So this is the kernlab package. I'll load the kernlab. Installed. So when I'm doing this, when I'm loading the kernel lab package, there's no package called kernel lab. Let me do an uninstall. I'm not having the kernel lab package as well here. Mm, So let me try removing this package first. So let me call remove dot packages, wherein I have to give pkgs is equal to name of this package kernel lab. First let me try removing it and then let me reinstall it again. So it's not finding this package as well. So that's the reason the kernel lab is not coming out. So let me just try for one more time. So now let me try the installation once again, but I think the problem is still continuing. Let me stop this. Let me save the workspace so that I can use it again. Library kernel lab. Okay, looks like now the things are better. So Yeah, now the kernel lab is loaded. So let me look at the variables, whether they are loaded or not. Dim stock saying okay, 1712 rows, 9 columns. I can look at dim stocks 1 also, which is containing 5 columns. So I'll use this stock. Let me use the head of stocks to quickly see. Okay, this is fine. Head of stocks 1 also, this is fine. So now what I'll do is I'll go ahead with my KK means algorithm, right? So let me use model 4. The model 4 is using KK means, and let's see what is KK means doing. So I'm doing what is KK means doing out here. A weighted kernel version of the famous K means algorithm. We have already talked about it. Right? X, the matrix of the data to be clustered. Symbolic description of the model to be fit. A kernel matrix of class kernel matrix or a list of character vectors. So I can very well take it as a matrix. Let's see without matrix will it take or not. So the data, okay, I can give the data. I don't need the data here once I give the X, which is the kernel matrix. Centers, I'm going ahead with 3. So based on that, I can use different kinds of kernels out here. Kernel provides the most popular kernel function, so I can use any of these kernels. So by default, it takes RBF dot, but I can very well go ahead with various other methods of kernels itself. And the algorithms, I can use KK means or even Kernighan algorithm. So we'll use the KK means only because the process that we are going ahead, the default itself also is the KK means algorithm itself. So let me go ahead with the KK means part, model 4, wherein the default is RBF dot. So let me go with KK means. I'm taking my stocks 1 data, and I require the centers. Let me take the 3 centers itself and the kernel. So right now if I ignore it, it will do it based on RBF dot. RBF dot is nothing but radial basis kernel, which is a Gaussian assumption. Otherwise I can go with a polynomial kernel or vanilla kernel or hyperbolic tangent kernel. Any of those we can very well try out all the possible scenarios. So I have given RBF dot as the kernel, and all other things is pretty much fine. So let me go ahead with the implementation of this particular model. My model 4 is getting right using automated sigma estimation for RBF. So I can type in my model 4 to see what this has done. So this is how it has given the cluster membership, right? And I could see that the centers are something like this, and the cluster sizes are too much different out here. 318 is the cluster size for the first group, 515 is for the second, and even 879 is for the third. And within the cluster, sum of the squares is coming out to 47. 47 within the cluster, the sum of the squares is coming out to 47 for the second cluster, 329 for the first, and the 7964 for the third cluster. So these are the clustering groups that it has come out with, and I could see that on different dimensions these are the cluster centers, and I could see that the clusters are not that very heavily differentiated, also may not be a good cluster fitment altogether. But let's say, let me try one more. Instead of using RBF dot, let's say I want to look at another kernel, which is TANH dot, where I'm going with the hyperbolic tangential cluster. All right. So let me see what is coming out here. With this kind of a clustering algorithm, I could see that model 5 is doing a different clustering. 389 is in the first cluster, 805 is in the second, and 515 is in the third. So again, different kinds of clusters are typically getting created. The cluster sizes that are coming out here is completely different from the cluster sizes that we have got in all the other three cases. But yes, I can very well combine this also as a part of my data, see which kind of cluster groupings have really broken the overall data quite significantly. So I can very well say model $5 model $5. So let me look at the structure of model 5. So I could very well go with the data. Model 5 dot at data is something that I'm more interested in looking at. So let me call model 5 at dot data. So this is what it is. So what I can do is I can do stocks dollar kk means is nothing but model 5 doll at the rate we use for S4. So at the rate dot data. So which is doing the allotment. Now I can very well look at the head of stocks to finally see which ones are doing the grouped into which kind of clusters. So that's how I can use different kinds of partition based clustering algorithms to partition your data. But one main thing that we have to understand, whatever is the mechanisms, right? I can also visualize the result. I can do a plotting of any one particular variable. If I want, I can even plot any particular variable. Otherwise, let's say I'm plotting the whole stocks 1 across the number of clusters, right? The columns I'm taking it as model 5. Based on the model 5, I want to look at the plotting of the stocks. Now I could see that this is how the stocks have been quite spread out, all of them being the numerical values. This is how I see that they have spread out, right? Otherwise, I can do the plotting of one single variable, stocks $1. Let me plot for change, or let me plot for the total traded value, right? I will take it as stocks $1 total traded value. So this is invalid for atomic vectors. So I have, or probably I can now very well take column is, I'll take it as model 5 at the rate dollar data. Still I'm having a problem. So okay, I have to plot it across for all of them, which is not giving me a good picture. So I can take only the selected columns, if not all of them, right? One way is I can only take the selected columns, and for those selected columns I can look at the plotting of the same. So I can very well consider only those specific points otherwise, but my overall plot is coming out this way when I am going ahead with the plotting for the overall data. So I could see that so for some of them the change is going to be much higher. For some of them the changes are very much on the lower side. So that's how the clear breakup across the clusters is typically occurring. So the main intention of cluster analysis is look at your data, break down, and finally try to do the grouping of the data based on the various attributes. I hope you got a clarity on different kinds of clustering algorithms that we have used. These are all partition based clusters. If you have any further queries regarding the same, please feel free to get back to me by giving me a call on the number that I have given below, or even you can send in an email at the email address provided. Thanks a lot for listening to this session. Thank you very much.